Right, hello guys, good morning all. Hopefully we're all alright, and we are doing okay. Sorry about that. Just removing something from a playlist. Okay, so this morning gonna review electromagnetism. We're going to review some of the bits and pieces of the workbook. I've got in front of me, guys, the live chat, so I can see what guys are asking. If you've got any specific questions about the stuff I'm going through today, going to do probably about half an hour, something like that, and see how far we get. If we get to a good place to stop, then that'll be good. Otherwise we'll keep going if people want to. Now, so this is the booklet that we are doing. Going to look at this. This is the one I've sent out. Should have received it. If you didn't receive it, then please let me know, because a few people have struggled with it. Likewise, if anything during the chat can't hear me, something's not coming through properly again, please let me know. Right. Okay, so onward then with the booklet. So what I've done is put this booklet together. Like I said, not going to go through all of it, because this booklet was meant to last really till the summer. This is all the work Year 10 had left to do. Once we've done this, I'll be giving out a past paper for Year 10 to do based on this, as a bit of a test, as well as with Educate. So with the booklet then, couple of things. I'd have either printed, personally I'd have printed it off, written on it, take photos of it, scan it back in. If you're going to do it on the computer, I would suggest that you download it. Don't edit the one that's in the folder, otherwise everyone else can see what you're doing. So save it to your own user area first and then re-upload it afterwards. Alright, so booklet then. First page, smiley face page. You're used to these, we've done quite a few this year. So keep going, let's say, same idea as what we've done in the past with these. Alright, so you complete your smiley face page to repeat it. Now, helpful YouTube videos and some helpful websites to guide you through some of these bits and pieces. Two down the bottom, you've got Seneca and you've got BBC Bite Size there. Both of these really useful for what we're doing. Okay, on to the first piece of work then. So, use of internet. Use the internet and revision guides to complete the following magnetic field diagram. So those two websites will help. Alright, so these websites will help. So you're on those two websites. I have those two websites loaded up. So what we have got is the first one is looking at bar magnet. Just try and refocus my camera slightly. Is that better? And then the second one is looking at a current carrying wire. Now, a couple of symbols that are new to this. So we have this one, which is this symbol means that the current is coming out of the page. So you can think of this as current that is coming towards you. The way I always like to think about this is, a bow and arrow. This would be the arrowhead pointing up. We're looking at our field lines of our different different things. So we've got bar magnet. We're now going to look at current carrying wire. So to do that, we go on to this one. So this is the other link, magnetic field wire, current carrying wire. So this has got current. Now, conventional current flows from positive to negative. So This is the current coming up out the page. So we're looking on this diagram down into it. And you can see that our field lines, we can plot them as we go, but you can see that our field lines, if we were looking down on this, then our field lines would be going anti-clockwise. So we can draw a whole bunch of circles, and that is our current carrying wire and our field lines for that. So Lara, have you managed to get on Teams? Sign into Office 365. Go on Teams. Managed to find it now. Hopefully. If you cannot, it is also in that GCSE physics group. So that's accessible on SharePoint. So if we go to SharePoint, there will be one that says GCSE physics. You go to Documents, Electromagnetism, and if we search this by modified, newest to oldest, it's not there, and it should be. Okay, let's make sure it is there now. So I'll put that into that folder as well. So that's in electromagnetism. Cool, right, so people have got it now. Yeah, so it's in that on GCSE physics as well, so that's handy. Alright, so we've got these two. So we've got our magnetic field of a bar magnet, magnetic field of a current carrying wire. So we're now onto a solenoid, or a coil of wire, and we haven't been given a link for this one here. So if we want to find this out, that's all we just put in. Magnetic field, shape, solenoid, or coil of wire. And we can see the different shapes that come up. So we'll go for this one. There we are. So here is our wire. We've got the opposite way round to this because we've got current coming in this end and going out that end. So our lines are going to go the other way around. So the one's going through the middle, like so. And then we're going to have them looping round on the outside. Let's just complete this up. There we are. Now, what does this look like? That's interesting. Compare it to a bar magnet. So our solenoid and our there's our solenoid. So our solenoid is very, very similar to our bar magnet, which leads us on to our rules. All right. So our field rules. So magnetic field, or the B field lines, always go, let's just put this work back up on here. Okay, so B field, so the shapes you should have. Just realize that wasn't on the screen. All right, so those are the three shapes you need to know for this section of the exam. So you need to know that bar magnet is that shape, a current carrying wire is that shape, and a solenoid looks like that. Okay, so for our field rules then, so field rules, these are how we know what is going on here. So magnetic field, called a B field, as far as I can tell. I do not know why it's called a B field. There's been no, if you look it up, it's basically just the people who came up with this just went, yeah, I feel like calling it a B field. No more than that, they've just literally made that up. Okay. So, lines always go from north to south. In a current carrying wire and in solenoid, we use Maxwell's corkscrew rule. Use it slightly differently for each one, but it's basically the same hand movement. So you use your right hand, you put your thumb in the direction of the current, So thumb in the direction of the current, and the fingers curl round to show which way the field lines are going. So if we get back our current carrying wire here, our current is coming out of the page, and our field lines curl round like so, showing us the anti-clockwise direction. We can also use a similar idea for a solenoid, but we swap it round. So for a solenoid, our fingers go in the direction of the coils of the current. So here, the current is going up, and our thumb, which way that points, tells us which is the North Pole. So for our solenoid here, this time our current is going from, the coils are going this way round, so our fingers need to coil round up, and our thumb points to the right. So on this one, if we want to label them up, this is the north and this is the south, which if you look at this diagram with it, they're going in opposite directions. So the poles will be the opposite way around. Okay, so the force on a current carrying wire. Alright, so this website, and follow the instructions on it. So let's go to that website. Okay, so this website's now loaded up. So we've got the Lorentz force, and it's just loading up. It's named after, Hendrik Lorentz, who did a lot of work on it. So if we read through the different bits, we can experiment. So we can shut the knife down, shut the switch down. We get a direction of current flowing, and we can see that this little bit of wire moves. And we can show the different field lines interacting and why we get that. If we flip the battery, it moves the other way. If we flip the magnet, that moves the other way. So we start to see what things affect the different rules, different things. And we're now going to come on to this left-hand rule. So Fleming's left-hand rule. And this is one thing with this exam not going ahead. You lot missed out on the magic physics handshake, and everyone else looking at you funny in the exam as you do it. So Fleming's left-hand rule. So you take your left hand, let's zoom out a bit with this camera. So you take your left hand and you put your fingers in this orientation. All right, so your thumb, your first and your second finger are all going in different directions, and your thumb is going to be the movement or motion, is what we go with that. Your forefinger is field, so that's magnetic field, and your second finger is for the current. Other people use FBI, force, B field, current, but the thumb for motion, forefinger or first finger for field, and second finger for current. Okay, so this is what we got. So Fleming's left-hand rule helps us to decide the direction of the force, the current, and the magnetic field. But if we want to work out the magnitude of this force, then we use this formula here, F equals BIL. All right, and as it's written, F is force in newtons, B is the magnetic field strength in Tesla. New unit, so unit of magnetic field strength is Tesla, obviously named after Nikola Tesla, who did an awful lot of work on this. I is current in amps, and L is length in meters. So it's important that you always work in those units. So newtons, Tesla, amps, meters. Quite often these things will be given in like millitesla or millimeters, centimeters. So it's important we get those changes. Okay, so we're now going to do some practice, and I'm going to go through these answers for you and show you how I would go about this. So use the equation. So remember, our equation is F equals BIL right at the top, so we know where it is. write down the formula for the force on a wire length L placed at right angles. So this is just writing down the formula. This first question asks us just to write down the formula again. A pivot arrangement using a wire length 15 centimeters is placed in a magnetic field. When a current of 4 amps is passed through the wire, it is found that a mass of 2 grams must be hung from the wire to return it to a horizontal position. Alright, calculate the magnetic flux density of the wire. Okay, so there's a lot of words there, which probably don't make sense to begin with. So, how do we go about that? What to do? Well, first thing I would do is probably try and draw a little diagram so we know what is going on. So we've got a pivot arrangement. So basically all we've got is a wire on a little pivot. Okay, so we're passing through this wire 4 amps of current, and we've got some sort of magnetic field here, which is going to cause our wire to move down in this direction, and we hang off this end 2 grams, and that balances it out. Okay, so in terms of the force then, so the force of magnetic field, the force needed to balance this up, must be the weight of these masses. So we do 2 times 10 to the minus 3, so this is to put it in kilograms, times 9.81 gives us the weight in newtons. So that's 2 times 10 to the minus 3 times 9.81. Press your SD button to get the right to get it in a number, and we get 0.0196 newtons. Okay, we want magnetic flux density, which is B, so we get B equals F divided by IL. Now we put the numbers in, so we've got 0.01962 and then we divide that by the current, force, and we times that by the length, 0.15. 0.15 because we need it in meters. Like the comment, Johnny Sins. You know that I never sign them anyway, so just take your planner with you, it'll be alright. Okay, so we do that, we put that number in, so we've got our 0.01962 divided by 4 times 0.15, and we get an answer of 0.0327 Tesla, which would be 30 millitesla. Which will do. We don't need to go to any more precise than that, because we've got 4 amps, so that's to one significant figure. We're probably 2, so perhaps 33 millitesla is perhaps acceptable as well, but that would be okay. Right, horizontal wire 6 centimeters long and mass 1.5 grams is placed at right angles to a magnetic field. Magnetic field. The flux density 0.5 Tesla. Calculate the current that must be placed through the wire so that it is self-supporting. So this is basically, we are floating a wire inside a magnet like so, and we want to generate a force that makes this wire float. So the force we need is again 1.5 times 10 to the minus 3 times 9.81, so that's the force we're going to need. Put those numbers in our calculator and we get 0.014715, and we want the current, so this time we want I. So I is going to be F over BL. So 0.014715 divided by B, 0.5, times by the length, 6 times 10 to the minus 2, to put it into meters. Put those numbers in our calculator. And we're going to get a current of 0.4905 or 0.50 amps. 0.5 amps. In terms of the decimal places, that's fine. I don't tend to look at decimal places. I'm going to look at significant figures. Alright, so as long as your answers, WJC don't actually care. WJC don't actually care about a GCSE, your accuracy, as long as you round it correctly. So whether it's 2 decimal places, 3 decimal places, that's fine. As long as when you round correctly. So if you left your answer like this, that's fine. 30 millitesla is also fine. 32 millitesla would have been fine. Sorry, 33 millitesla would have been fine. 32 wouldn't be. For this one, just leave it as 0.4905. That's fine. That would work. 0.5 again doesn't really matter. I'm only going to 1 there because of the 6, because of the 0.5. Those 2 numbers there are only only one significant figure. Right, question 3. A wire of length 0.5 meters carrying a current of 2 amps is placed at right angles to a magnetic field of 0.2 Tesla. Calculate the force on the wire. So we got force is field strength 0.2 times current 2 times 0.5 for the length. 0.2 times 2 times 0.5 is 0.2 newtons. Does that answer make sense? Yeah, because the 2 and the 0.5 times by 2 and times by a half are inverses of each other. So that makes no difference. So yeah, 0.2 makes a lot of sense there. Okay, questions 5 and 6 relate to the same. No, don't relate to the same. Ignore me. So, yeah, same field. So, magnetic field exerts a force of 0.25 newtons on an 8 centimeter length of wire carrying 3 amps. So, our important numbers. Calculate the force on the same field we exert on a 20 centimeter long piece of wire. So, a couple of ways of doing this. Firstly, we can do it the workout B. So B is F over IL. So that's going to be 0.25 divided by 3 times 8 times 10 to the minus 2. So that gives us a B field of 1.0416 Tesla. And then what we do is we go force is B times I times L, and we put in our answer for B times 3 times 0.2 or 20 times 10 to the minus 2. And we get a force equal to 0.625 newtons, or 0.63 or 0.6. All of them would have been fine. The other way of doing this is because field strength and current don't change, F is proportional to L. So the other way of doing this is doing that 20 divided by 8 is 2.5, and you multiply 0.25 by that number, and you do it that way. Both ways are acceptable. It doesn't really matter. This way is probably easier to do at first, but the other way is quicker. Alright, to calculate the force the same field would exert on 3 insulated wires, each 20 centimetre long and held together parallel to each other. Right, well, I've got 3 wires, each carrying 3 amps. So I've got a total now. They're all going to experience the same force. So I'm just going to have 3 times 0.625. Which is 1.875 or 1.9 newtons. Why is that? Well, each wire is going to get pushed up by the same force, but because they're parallel to each other, they're going to all push up with that force. That force is going to combine. Okay, so the next page, because mine has got slightly out of order, is the electric motor. So this is probably, I'm going to finish on electric motor. So we're going to have a look at our electric motor. This is going to be the last thing I'm going to go through today, because we've already been about half an hour. Don't want to go much longer than this. Plus then that means that we've got inductors to do this time next week, and we can do induction and transformers together this time next week, and it gives you a chance to do this end bit. So alright, so we go to the link on this page. Let's load up that link. Okay, so we go to the link. There's the link. Label the diagram of the electric motor and show the direction of the field and the current. Thanks very much, Johnny. Hopefully this is, I said, this is a lot of new stuff. This topic is probably one of the hardest in year 10, so for us to miss it out was a bit of a shame, but it's also one of the most rewarding because it explains an awful lot of stuff about electricity. Okay, so we look at this diagram, we label this diagram. So we need to label the magnet. We need to label, this is a coil. These bits here are called brushes. We can label the cell. And then this device here is going to be our commutator. We need to show the direction of the magnetic field, so I'm going to do that in red. Magnetic field goes from north to south, like so. So these lines are B field. And in black, I'm going to show the current. Now the current is going to come out of, we'll do it in blue actually, sorry. Going to come out of the positive. So it's the current is going to go this way round in our wire. Okay, so what is the point of the split ring commutator? So if you look at our electric motor, you can do some work yourself, but if you look at the diagram here, let's have a look at the diagram a bit closer. Oh, that didn't work. Come on, right, there we go. Right, so we've now got the diagram a bit closer. So you can see this is our commutator, this bit here. And what is happening is as this spins, it's reversing the direction of the current in the wire. So at the minute the current's flowing this way around this piece of wire, and now it's flowing the other way around. So the point of the commutator is to reverse the current in the coil every half turn, and that just means it keeps spinning. What would happen if there was no split ring commutator? So if we didn't have this device here, what would happen is our coil would end up, so all that would happen is our coil would end up getting stuck at right angles to, would end up at 90 degrees two magnets. So if we didn't have it, all that would happen is this would spin round, and eventually it would get stuck in that sort of position and it wouldn't turn anymore. Because here all the forces would be balanced, and yet it wouldn't spin anymore. How could you work out the direction that the motor will turn? So we use Fleming's left-hand rule. It doesn't matter which way round it goes. Well, for quite a lot of things you need a motor to turn in the right direction. So yes, you need to be able to tell, is that motor going to turn in the right direction? So we use Fleming's left-hand rule. So on our diagram at the top here, Fleming's left-hand rule, our thumb is the force, that's the one that we're looking for, the motion. Our first finger is our current. So first finger is field. So our field is going from left to right. Our current, our second finger is going this way. So our motion in this one, this side's going to get pushed down and this one's going to get pushed up. And so this is going to come over the top. So as we're looking this, if we're looking from the view of the cell, this is going to turn anti-clockwise. Okay, what affects how much force is acting on the wire? Well, the current, the length of the wire, and the strength of the magnetic field. And you can do that here by, that's just going to change the spin. But yeah, going back to our formula, F equals BIL. Okay, what is the energy change in our electric motor? So we are taking electrical energy and we are creating kinetic. Okay, what are the three ways to increase the speed at which the electric motor changes? That should say spins. Well, we can increase the current. Increase current. Now it's important because it says increase the speed, we need to put that in there. So we increase current. We can add more coils, or we can have a stronger magnet. All three of them are going to change how fast our motor spins, because more force means it's going to spin quicker. Okay, it would help if I've just realised I've gone through all of that and you didn't see what I was writing. So I'm going to put up what I was writing there, so you can see on here. This is what I was talking about using Fleming's left-hand rule. So just go back through that again. So Fleming's left-hand rule. We want that one. We don't need the website now. So Fleming's left-hand rule on this motor. First is fields. The field goes from left to right. Second is current. And the current is going up on this side. Thumb is motion. So this is getting pushed down into the page. On this side, the field is still in the same direction, but the current is reversed. So the motion gets pushed up. And it spins then this way around. So our motor is going to spin this way around. And yeah, so we use Fleming's left-hand rule. This, how much force is acting on the wire, this goes back to our F equals BIL. And them in. Our energy electrical to kinetic. And to increase the speed, we'll increase the current, we'll put more coils, or we will have a stronger magnet. Alright, so that brings us to an end of the work that I wanted to go through today. In order to go through some different bits and pieces, want to discuss then the website. I've realised I've disappeared again. There we are. Right, back again. Okay, so I want to go through some stuff that, like I said, was there to help you on this. So, like I said, if you go to Microsoft Teams, Teams that you're a member of will come up on here, either 10A3, 10A2. So those are there. In both of these, in the documents, there is this workbook. But the main place, if you go to SharePoint, so let's just go back to SharePoint. So go to SharePoint. You will get the SharePoints that you're a member of, including your teams down here. But if you don't know, I can't see anything, GCSE Physics, like so, click GCSE Physics. There is a link to the WJC website, a link to a revision prezi with all this stuff on it, link to revision guides, but the best bit is go to Documents, go to Electromagnetism, and in here are all the resources that here are all the resources that we would use in class to teach this, along with this document, to help you with that. What else is available to help you? So, educate. Oh, I didn't click stay login. So, educate them. As you can see, only 5 people so far have done the thing, but that doesn't matter. This is end of topic. So, this is designed for the end of the topic. We're only halfway through this topic in terms of what I've gone through. So don't worry so much about doing the educate yet. That is coming. So in terms of Isaac Physics, don't forget, I know with my classes I've gone through this. I haven't set any assignments on this yet, but there are, if you go to questions and you go to fields and we go to magnetic fields, there aren't any questions. You're in luck, there aren't any questions. Because this is designed for A level. So there probably won't be any questions. Let's just check. Let's just check from the books. Mechanics, electricity, generators, resistance power transformers. No, you're in luck. There aren't any questions so far on this at a level that you can do, but there are some for what's coming up. Alright, so thanks for watching. Like I said, stay safe. Make sure that you are following all the guidance. Keep up with your work. If you get anything, if you're getting stuck, remember, email me. If you want me to check work that you've done, email me through the document. I can have a look and I'll send it back with some comments. And probably next week we will do some, go back to doing some Kahoot quizzes. Perhaps I'll do some Kahoot quiz on this work. Okay, right. So, like I said, thanks for watching, and I will see you next week.